I work at Netflix. Has anyone seen Stranger Things on Netflix? A Netflix original? All right, so a bunch of people have. Stranger Things has a character in it, 11. And not to give away too much of it, but 11 has superpowers. And as part of the story, 11 determines what she's capable of, but she's not certain, and grows and enhances her superpowers throughout the series. It's exciting, and I feel we're in a similar stage with enhanced BPF. Enhanced BPF gives developers these superpowers, but we don't even know everything we're going to do with them. You can do some really crazy stuff with enhanced BPF, as you'll see. So we're in a similar stage. It's a great place to be if you're interested in cutting-edge operating system research, because you can come up with some crazy ideas and then implement them in Linux using EBPF and run them safely in production. Just as one example of many, here's a tool I wrote called TCP Life. TCP Life tells me the TCP sessions that are happening on the box, and it will tell me the process ID, command, basic details, and it will also tell me the transmit kilobytes, receive kilobytes, and duration. And this has very, very low overhead. I'm not tracing. If I showed this to any network engineer prior to BPF and dynamic tracing, they would say, oh, sure, I can pipe the output of TCP dump and write your program. Although, how do you get the PID and command from TCP dump? Because it doesn't know that stuff. I don't want to run TCP dump on my production servers because that instruments send receive. And send receive on 10 gigabit Ethernet networks can be very busy. So this actually uses BPF. I'm only touching TCP set state, which is when TCP sessions change their state from SYN receive to established, because that's a lower frequency and low overhead approach. And since I'm tracing in the kernel, I can pluck out whatever I want. Process IDs. Fortunately, there are bean counters for send and transmit kilobytes, and then duration of sessions. So suddenly, I just made up this tool and I wrote it and it works. I can now take my tool, which is written in EBPF, and I can run it on Facebook's production servers and anyone who's running more recent kernels without changing the kernel. If I talked to you about this before EBPF, you'd say, well, I'm a kernel engineer and I can just change the kernel. Well, you can, but to come up to Netflix and say, hey, I've got this really cool thing I want you to try, you have to run my kernel patch set. It's like, well, that's going to take some time. I mean, we are fairly risk tolerant because of our architecture, but we still have to do a kernel build, and then we have to deploy that new kernel. With eBPF, you can do all sorts of kernel engineering on a live kernel. So I just run an eBPF program and I start doing kernel stuff. So this is why eBPF is kind of like magic. It's a superpower. I've been creating observability tools using eBPF. So many of these are mine. These are open source. This is part of BCC. I'm going to talk about eBPF and BCC. I'll show you some of those tools and then talk about future work like visualizations. Hopefully you will understand Linux tracing components better, understand the role and state of enhanced BPF, and discover opportunities for future work, of which there are many. I work at Netflix. One thing I want to mention is who will use BPF, enhanced BPF at Netflix, and it's a fairly advanced technology to code in directly. I think a lot of engineers will be end users of performance analysis GUIs that use eBPF as a backend. So a lot of people will use it without getting their hands too dirty. Some of the engineers will get their hands dirty because we're creating new tools and other projects. Security is using eBPF for doing intrusion detection. So a whole different use. So introducing eBPF. BPF itself comes from Berkeley Packet Filter. It's this obscure technology from the 90s where we speed up TCP dump, because TCP dump has to operate on every packet. And I can give it an expression like TCP dump this host and this port. And what happens, although you probably didn't know it, or maybe you did, that'd be great, is that expression is compiled into BPF bytecode and sent to the kernel, and the kernel runs it in its own virtual machine, a BPF virtual machine that's been part of the kernel for a long time, so that it can efficiently execute that expression on incoming packets. And so it can do filtering early, and then when TCP dump is reading from its buffer, it's already being filtered efficiently. Great. Seems like a very boring technology that only a few people would get excited about, except I said the words virtual machine. So there's a virtual machine in the kernel. Think about it. I can write programs, and I can have the kernel run my, in fact, I can run TCP dump. The kernel's running my user-defined program. So some engineers did think about this a lot, especially Alexei Starotov, who's the lead developer, and he realized, let's enhance BPF to do much more things. And so now we have this much more powerful sandboxed virtual machine in Linux that you can write a user-defined program and have the kernel go and run. Previously, like I said, if you want to do kernel stuff, you might say, Brendan, here's my patch set, please run it. It's like, oh, I don't know. Or you might say, here's my loadable kernel module, please run it. If you made a mistake, you'll panic my servers. If instead you said, hey, Brendan, here's my EBPF program, I'm much more comfortable running that because that's in a sandbox virtual machine. It's not going to negatively interfere with the kernel. And so there are lots of vendors who do performance monitoring products or whatnot where they have various kernel agents they want you to run. You have to run our kernel agent on our system. We're hoping that all of those over time switch to eBPF. And so that kernel agents become a thing of the past. And they become these sandboxed, optimized, safe programs in restricted eBPF. How it works? So for an observability program, I have my BPF program. That gets compiled into BPF bytecode, loaded into the kernel. The kernel may reject it in a verifier. The kernel may say, oh, you're doing something naughty. You're not allowed to access that memory in that way. If it accepts it, I can then attach that program to events. So tracepoints, dynamic tracing for kernel and user level, sampling and PMCs. BPF has efficient ways of bringing data back to user level. So I have per event data which goes through a ring buffer, and I can read asynchronously. It's actually using perf events ring buffer, so it's optimal. But it also has these things called maps, which are associative arrays. And in maps, you can do things like histograms and heat maps. And again, I can asynchronously copy them and generate my own in-kernel summary statistics. So I'm not dumping everything to user level. If I'm observing things, I'm able to use BPF to do, because it's a program, right? I can write a program, I've got associative arrays, I've got data structures. I can do that summary first and only read the summary from user level. Dynamic tracing is a key part of this. Dynamic tracing is what lets us attack any kernel function or any user level function. Dynamic tracing comes from University of Wisconsin-Madison, and Professor Barton Miller and Associates did a paper on it, 1994. And they also did an implementation, kernel's paradigm, which worked. And this has been picked up by the industry, and Linux initially did a version of it in 2000 with kprobes, which never got integrated. Sun did a version of it in 2004, 2005, called dtrace. And Sun did a really good job. Dtrace was production safe. And that's remarkable for technology. How dynamic tracing works is it will live patch instructions with instrumentation. So instead of calling this function, it could be any kernel function, there are tens of thousands of them. With dynamic tracing, I say, change the instruction prologue to go to a soft interrupt and run my instrumentation and then do a ret. Can you imagine changing instruction text live on a system? I've had to do it a few times in debuggers, but that was like a very big state of desperation. You know, if you mistype something, you'll immediately panic and crash the system. But the dtrace showed that it could be done safely if you engineer it really, really well. That's a very important turning point for the technology, as this went from a really cool research project that showed a lot of promise to something that people trusted to run in production. I was involved with using dtrace, and I did a lot of dtrace contributions, like the dtrace toolkit. Just to compare the new world of dynamic tracing with the old world. So that was 2005, and Linux has added dynamic tracing since then. The old world, let's say I wanted to look at TCP retransmits, I might run TCP dump, get a packet capture, I have to write that out to disk, and then post-process it. The new way is I just go dynamically trace the kernel function that does retransmits, and it's very low overhead. I have a slide. Again, these slides will be online. This shows the Linux events and when BPF supported accessing them, similar to my slide from earlier. So you can see that we started to get access in Linux 4.1 with kprobes, and by 4.9 we had everything. So if you deploy on a 4.9 on your kernel, it's great, because you can run all these tools. And I did mention this briefly, so there's the Linux tracing timeline from prototype dynamic traces to where we are today. And EBPF is relatively new. EBPF builds upon the prior technologies. So it builds upon some work Linux did with kprobes and uprobes and perf events. BCC is a front end for BPF. So I've got a block diagram here. With BCC, it provides a Python front end, a Lua front end, there's a C++ front end. You might want to add more front ends. That would be a good project. You might come up with a better one. And then it has libraries that make calling BPF and programming it easier. It's on GitHub, it's open source, it's part of the Linux Foundation. To really explain why we need front ends, this is raw BPF. It's kind of hard to program in. I've done lots of assembly level programming, but this is not x86 assembly that there are plenty of resources for online. This is its own assembly, which there's basically nothing on Stack Overflow to help you. Of all the languages I've coded in, and I've coded in crazy ones like intercal, BPF is the only language, raw BPF is the only language that's defeated me. I've failed to write a working full program in raw BPF. And it's difficult. Like I said, there's not really many examples of this because it's its own new thing. So it's really hard. Alexei Storotov, who created it, he can write these in his sleep. And so if I need something written, I'll send him an email. But it's hard. I mean, if you want to learn how to do it, that's great. Just saying, it's challenging. Fortunately, you often don't have to. So Alexei did code in a C interface. And so by using the LLVM compiler, it can take some C code and then convert that into the BPF instructions, the BPF bytecode, which is great because I have written lots of these C-level BPF programs. But a problem with that program is I can only put a portion of it on the screen at a time. This is from the kernel source code, samples BPF. I had to truncate 58 lines. Here's the first BPF program where I can fit the whole thing on a slide. And this is because it's in BCC, and BCC gives us a front end that has an API for simplifying some things. So on the left is a Python program for doing the summarization, and on the right is the C program for, sorry, on the left is the C program for the summarization, and the right is the Python program for printing it out. So that's doing kprobe, block account IO completion, and yeah, that's right, this is doing a histogram of IO size. But it could get lots better still. dtrace proved that you can come up with a very concise, high-level language. dtrace is excellent. We don't have a complete one for Linux yet. And there's been a couple of projects to try to do one. One of them's called Ply, which shows promise, but hasn't been developed for a while. But it's another area that someone in the room might be interested in, coming up with a language that's really concise to front this BPF runtime. For the first time in our industry, we actually have a problem in search of a language. I read Hacker News all the time, and there's so many languages created. It's like, why do we need this language? This just seems to be, but now we need a language. Where are you language designers? Your time is now. I need you to design a language and implement it for BPF. I've drawn a diagram that shows the different technologies, because it is actually quite confusing in Linux. There's been so many tracing technologies and how they fit together. Hopefully this diagram makes it less confusing. That was the point. but BPF is all the way to the right of scope and capability because it does so much. So BCC, to show you some of the capabilities via the tools, in the slides I do mention that if you are going to do performance analysis with BCC and BPF, use the existing tools first because they're free. They use kernel bean counters before you turn to the more advanced ones. And I did do a blog post on that. BCC is fairly easy to install nowadays. Again, it's all open source. And you get all of these tools so far. As a checklist of some of the commands, if you're going to do performance analysis with BCC, I've got a few here, and I can run, set up a virtual machine I can run. So I can run exec snoop, and I logged into that system from another window, and I've just used dynamic tracing to instrument the exec call and BPF to pluck out the arguments so I can see what's being run. It's pretty nice. ext4 slower is one of my favorite tools. ext4 slower will trace ext4 operations slower than 1 millisecond. Oh yeah, great, I generated some. I was hoping to. This is great because a lot of people do performance analysis at the disk I/O layer, and kernel engineers have done so much work to make disks operate asynchronously to the application. And so what the disks are slow? It's important to know for capacity planning, but if you want to understand why the application is hurt, it's better to instrument closer to the application, like at the file system level. And so ext4 slower, I'm instrumenting at VFS, and argument of 1, so only show me operations slower than 1 millisecond, then it prints them out. I can do user-level instrumentation as well. And so I'm instrumenting all bash cells on the system simultaneously, and I'm finding out what commands they're running. I'm spying on everyone. But the point is, you can instrument anything, anything that you can think of. You have this superpower. I might want to, a func count is another example of one. Let's do, oh, there's only 2. Okay, 44 functions start with TCP/S. And while I was tracing, it hit 4 of them. Is it going to let me do all of them, or is that too many? Oh, I can do all of the TCP. Oh, that's good, right? So I've just dynamically traced all of the kernel functions that start with TCP, and there they all are. Like flame graphs, this is great for exploring and understanding code because there's millions of functions, or millions of lines of code and many thousands of functions in the kernel, but now you can see which ones are actually executing. I can also do things like, if I'm wondering, how did we call current MSS? Stack count is another BPF program. I ignore these warnings. I need to kill these warnings. Stack count is another BPF program where you give it a function, and then it will frequency count the stack traces that led to that function. So if I want to know how did we call TCP current MSS, there's a stack backtrace. In fact, did I give it? Well, I should give this a switch so it emits it in flame graph format, so you can just pipe this into a flame graph. It's on GitHub. You can send me a pull request. But yeah, that'll be nice. So that I can run stack count of anything and then pipe it straight into flame graph and do a flame graph. So there's lots of tools. So exec snoop I demoed. ext4 slower is another favorite of mine. BPF can do histograms, so there's biolatency, and it's a power of 2 histogram. So great for identifying outliers. That's doing disk I/O. TCP life I had at the start of the talk. Get host latency is another example of user-level dynamic tracing. This one's looking at, say, DNS resolution calls. because it's always DNS. CPU scheduler run queue latency, another good target for BPF. So I can see if there's kernel scheduler issues. I've got several scheduler tools for understanding how well the scheduler algorithms are working. And you can write lots more tools. My process is to find a functional diagram and then to apply performance methods. There's an example from my last book on systems performance where I did lots and lots of methodologies. But the idea is, with a functional diagram, you can then pose questions of the system. You have a mental model. I can pose questions of the system, and then I seek answers. This is a big shift from how we normally do performance analysis. Before dynamic tracing, you do performance analysis by the vendor gives you tools, and you learn the tools, and you run the tools. Now with dynamic tracing, you get to make up the tools. So some people aren't used to that, and it requires a lot of thought, thinking about what ideally do I want? Where may there be blind spots? What's better to instrument? There are some advanced tools in BCC so far, like trace, so I can do more complicated one-liners, like trace sysread if the third argument was more than 20,000 bytes, and more powerful one-liners for doing histograms. So I think a key area of future work is visualizations, and I've been working on vector, so flame graphs based on BPF, heat maps based on BPF, that's where it's doing a histogram over time. In fact, there's one that's shipped in the Linux kernel source, traceex3, where it does a latency heat map. I first did latency heat maps when I was at Sun and did an article in Communications with the ACM on them, visualizing system latency. And they're really helpful because they can help you identify multimodal situations. So say disk latency, we have cache hits and cache misses, but also latency outliers. And with a heat map, you can see how that varies over time. So think of a heat map as just a histogram for each row printed. With BPF, I can do efficient CPU and off-CPU flame graphs, and in the first talk, I talked about them. And I talked about off-wake flame graphs. And so that's exciting. And to finish future work for BPF, BCC itself is an open source project. There's plenty of things that hopefully we can improve somehow. So there are challenges with using it, initializing. You have to initialize all variables. Sometimes there's extra BPF probe reads. If you write a program and you start to dereference kernel memory, BCC tries to turn that into a series of BPF probe reads. A BPF program can only read memory via this one gating function, BPF probe read, which does all the security and safety checks. So you think in your program that you're dereferencing random stuff in TCP, but it's actually getting mapped to a series of safety BPF probe reads to pull in those bytes. And sometimes BCC gets confused and you have to do the manual BPF probe reads. And there are other challenges with it as well at the moment. I mentioned this earlier, but we actually have a problem in search of a language. It'd be great to have a higher level language for BPF. And over time, people will have a growing need for this. Because like I said, all the BPF observability features only made it into Linux 4.9. That's very new. So a lot of people aren't even on 4.9 yet. But they will be, and when they are, they will want to use BPF and higher level languages. Ply, and I had a slide of it earlier, is one person's effort to create a high-level language for BPF. He hasn't done development on it for a while, so it looks like that's not happening right now, which is sad. Maybe you want to help out. Just to show what Ply looks like. Ply kprobe this function and then run this printf. Or I could do kprobe sysread, store a timestamp in this associative array keyed on the thread ID, fetch it when on the kret probe for return, and then do a histogram of the time in sysread, just dynamically. There's likely to be many more tools and metrics that will come up with BPF and BCC and Ply and whatever other front ends people develop. And it's an area that I'm comfortable doing. I've done dynamic tracing since dtrace in early 2004. But a lot of people haven't, and they don't have the mindset of thinking about posing questions of the system. And it's tricky if you haven't done it. So if you have the time to forget about what the system's giving you, forget about those counters, and think, what ideally do I want from the system? Okay, then you go create it with a dynamic tracing tool. So it's a great opportunity for that. In fact, it's also an opportunity if you think about it. I mean, a lot of the metrics we have in operating systems come from like the BSD days. They've been there for decades and decades. If you think about it and say, you know, we can do better. Here's a better set of TCP metrics, and here is a better set of IP metrics. You can prototype them in EBPF. You could actually convince companies to run it because it's a sandboxed program. And once you've proven that these metrics work and you have case studies, you could then just code them into the kernel. So EBPF could be used to prototype what will ultimately be standard kernel counters. Helps you get case studies. So new visualizations, I talked about that in the first topic. So off-wake flame graphs or chain graphs to match waking stack traces with block stack traces. Another area of future work is we do need case studies published. That's how a lot of people learn technologies, is case studies. And something magical like the BPF Superpowers, we really need case studies to help people get their head around it. And it's on my to-do list because I'm using it at Netflix, and I know Facebook people are using it as well, and we're all pretty busy using it. Like, we need to stop and publish some things. And if you're using it, please publish some things as well. That's BPF. So the takeaway is understand Linux tracing components and the role and state of enhanced BPF. It's very new technology. It's a sandbox virtual machine. Do a lot of crazy things in it, but it's very, very helpful for prototyping new tools. And I talked about areas for future development. Again, these slides will be online. And that's my BPF talk. Thank you. So we have 10 minutes. Feel free to ask me questions on BPF or flame graphs, or to skip out early to get coffee, whichever of those three.
Hey, thanks for the talk. So your tools rely on hooking internal kernel functions, basically. So is the kernel community committed to maintaining compatibility? Like, if those functions change or the parameters change, presumably your tools would break. So what's the long-term compatibility story?
So dynamic tracing is awesome, except for when you've dynamically traced a bunch of kernel functions that change. And it's a big challenge because if you're lucky, the kernel engineer just renames the function and your program doesn't work. It's like, oh, I can't find, in fact, this just happened with ZFS. They got rid of ZPL read. And so my ZFS slower tool doesn't work because it says I can't find this function. What would be bad is if they changed the function in a subtle way that wasn't obvious, and so it's giving subtly corrupt data. That would be terrifying. So we need to keep checking that the tools make sense and the output makes sense. That's the way life is with dynamic tracing. It has this awesome power, but you have to understand that you're basically instrumenting whatever the kernel engineer thought to implement, or the application engineer as well. And there's no API guarantees that will work from one version to the next. That's why we have static tracing as well. And so in the Linux kernel, there are tracepoints. That's static tracing. They've been around for a while. In user level, there is static user level tracing. Dtrace was a really forcing factor for getting applications like MySQL and Postgres and many others to implement user level static tracing. And BPF can use those user level static tracing probes. So that's it. It's static tracing. And there is static tracing for block I/O for, actually, there's not really TCP yet. Scheduler events. There are a bunch of static tracing probes. Kernel engineers don't like adding too many static tracing probes because once they add a static tracing probe, that's now part of the kernel ABI, and they have to support it. I like it as a performance engineer because once I get to write a tool that uses a static probe, it's done. I'll never have to maintain it, right? It should work forever. But convincing the kernel engineers to add them. So I think there's going to be a balance. I think very common functions like TCP send and receive and TCP connect and accept we should have a static trace point. One doesn't exist for the TCP ones yet. Someone still needs to do that work. In fact, people are asking me to do that work, because I did that before for dtrace. But there's going to also be a lot of ad hoc things that are not common, and the overhead of maintaining a static trace point outweighs adding it. So like really obscure edge case things, you're probably always going to be using dynamic tracing for that. So that's to summarize that topic. Yes?
Hi, Justin Kapos, NYU. So this is really cool and interesting, and I'm coming at this from having used prior tools like ptrace and other things like this for a while to do different mechanisms. So I'm wondering from your perspective, which presumably you've used all the traditional tools, and now you're experimenting with this nice new, more general, more flexible, but also more limited in some ways, way of doing things. Can you talk about the pros and cons? Like, what are scenarios where you find yourself going back to the old mechanisms, and what are scenarios where, even though you could do the same thing with both, you end up using BPF?
So with the I like the old tools because quite often they will use kernel bean counters, kernel counters that are already baked into the kernel and are basically free to instrument. And so on my, as part of the slides, I have my Linux performance analysis in 60 seconds. That's all using standard tools, IStat, VMstat, MPstat, top, and so on. It's because the counters are there, they're free, so I may as well read them before I start turning on dynamic instrumentation. Because dynamic instrumentation does add a little bit of overhead, because you are doing extra cycles now that I've turned that on. So I won't use that first. So definitely use the old tools first, see if I get the low-hanging fruit out of the way. To use the newer tools, it's just to fill in all the blind spots, and there are many blind spots. A key area is VFS and file system tracing. There's no FS stat. Well, there should be. There's no, we've got TCP dump for the network interface. There's no VFS dump, which is why I've done the ext4 slower and things like that. At least there's block trace for block I/O. But for all these different areas, there's just many, many, many blind spots in this standard tool set. That's why I'll end up going and using BPF. If there are two tools that do exactly the same thing, why would I use the BPF tool? It's because I kind of need to customize it. Maybe I want to make it container aware, and the standard tool is not container aware yet. That's an example. Yes?
Very interesting. Nadav Amit, VMware. As someone who uses BPF, EBPF, I would like to know what are your thoughts. I use it as well, so I would like to know what are your thoughts about the maturity of the tool chain, of LLVM, of the verifier, and whether you would even consider letting someone who is not a supervisor run BPF programs in the kernel.
EBPF it's a pretty new technology, and it's required. There has been LLVM and Clang changes to support EBPF, so it can compile the bytecode correctly. It's coming along pretty well. We're using it in production at Netflix, although we have a safe fail environment. If I panic an instance, it actually doesn't matter because we use a library to have backups and whatnot. You may not have such a fault-tolerant environment. But it is being used at Facebook and Netflix at least quite heavily. Now, what was the other part of your question? So there was the last part was...
I asked whether you would let someone who is not a supervisor on a production system to run a BPF program. Would you consider the technology mature enough to do so?
At the moment, BPF programs can only be run by root users, and so that's an area we need to fix. There has been a little bit of work done for socket-level stuff. You can be non-root and do a socket thing, because BPF, the enhancements actually came from allowing software-defined networks. And so there was a lot of socket and networking things done early on. But it hasn't been done yet. Someone needs to do it. Someone needs to come up with the model to authenticate users, add a capability to Linux, et cetera, et cetera. So at the moment, you just have to be root. How does that work at Netflix? Like, we have very secure environments like containers. One easy way it works is the vector on-instance agent will go and do the low-hanging fruit reports. And so people click on the button, and it goes and runs a BPF program and gives them the output. So they're not SSHing onto the instance and running things themselves. This secure application is doing it for them. It's just one solution.
Ted Cho, Google. So just one sort of general request from the kernel community, which is that It is true that if there is a widely deployed tracing program that uses a static trace point and it changes, it is considered a stable ABI, and Linus will yell at whoever did it and will revert the change. He may also say, why the hell did you make such a stupid trace point? And the problem is there are a number of kernel developers that are adding trace points essentially for their own debugging purposes. So if there is functionality you need and it's not there, or there's a trace point that you want to use, it might be a word to the wise to reach out to the kernel maintainer of that area of the code and ask them if they could make that trace point stable, or inform them that you plan to be using it heavily, so that we can sort of head off problems at the pass, right? Because we will make good on it, unless there's like a security reason or something really awful. But we can sort of save a lot of trouble if there's communication between the tracing community and the kernel devs about what are stable trace points that you need, or can we actually depend on this on the long term? So just quick word of advice.
Thanks, Ted. And that's useful. And I'm using lots of static trace points. I've not reached out to developers because the static trace points I'm using, they're pretty common stuff. If I use something weird and esoteric, it should cross my mind that I should talk about it first. But I haven't used anything weird. But certainly, talk to the maintainers before using these a lot in
Yeah,
your tools.
if you see trace points of the form function name underscore enter, function name underscore exit, it's probably because they wanted to decode the variables in an easy way via ftrace, and that might not necessarily be stable. Then we could probably make something stable, but there are people who have not necessarily gone through the same thoughtfulness in designing, say, a new syscall as they have designing a new trace point. That's probably bad kernel maintainer behavior, but there are traps out there.
Yeah, and what I'd suggest is if you're designing trace points, do dynamic tracing first and make the use case and prove that it's valuable, and then add a static trace point to that dynamic place. I think one more question, we're done, right? One question.
Hello, this is Arvinda. I just wanted to check, how do you compare BPF with system tap? Because system tap also provides a lot of flexibility in terms of data collection and other stuff. So how do you compare BPF with system tap? So or how BPF is better than system tap?
So there's lots of traces on Linux. System tap versus BPF. System tap did lots and lots of great work with tap sets and integration. So in fact, we got uprobes out of system tap. It did integration into the USDT probes. It's figured out lots and lots of things. But system tap had its own compiled kernel module runtime that early on had safety issues and gave it a very bad name. So people are still spooked about system tap, even though it's very powerful. Now, the future, system tap, all the work they've done, the tap sets and the interesting framework, they can use that as a front end for EBPF. And so Red Hat engineer Richard Henderson, he's mentioned this on LKML. He's building up it's called a BPF compile target for system tap. If you're interested in that, please help him out, because that'll be great if that work gets finished, because suddenly all of the system tap work that they've done over the years now can just run on EBPF, which is sandboxed, safe, optimal, and that'll be great. And maybe that's another path to getting a higher level front end, is finishing the system tap EBPF backend.